All right, so this is part 7 of Unit 2, and in this section, or in this part of Unit 2, we are going to be kind of switching gears a little bit. We had been looking at polynomials and rational functions. Now we are going to be looking at exponential functions, and then in the next video, logarithmic functions. So this is a different type of function. It's not like a polynomial, it's not like a rational function. It works a little bit differently. The exponent rules that we learned at the very beginning of this course, back in the beginning of Unit 1, are definitely going to be necessary here. So you may want to brush up on some of those exponent rules and remembering what to do with a negative exponent, what to do if you have an exponent that's a fraction, how to work with all of those things. So exponential functions are of this form right here where we have a base and then our variable is in the exponent now. So before we were seeing things like this, 2x or should actually be 2 to the power of x here. Let me go ahead and fix that. 2 to the power of x. That would be an exponential function. Now we've been seeing things like this where we have x squared where our variable is in the base. But now what we're going to be seeing is our base is going to be a number and then our variable is going to be in the exponent. There's a couple restrictions on what b is allowed to be. It cannot equal 1 and it must be greater than 0, so it can't be negative. It can be a fraction, it can be a decimal, but it just has to be positive. All right, so here are some examples of exponential functions where we have a number and then our variables in the exponent. And then again, we can have a negative in the exponent. We can have numbers added or subtracted in there. We can have a base that's a fraction, numbers added or subtracted in the exponent there. These are examples of things that might look like exponential functions but aren't. Here, the base is negative, so that's a problem. That's not an exponential function. Here we have a variable in the base and in the exponent. That's also not an exponential function. Here our base is 1. Well, 1 to anything is just 1. That's not, again, it can't equal 1. That's not an exponential function. And then this is a polynomial, just x squared, like what we had been working with for most of the semester so far. So what we're going to do first is just kind of explore what these graphs look like. So first off, if we have the equation y equals 2 to the power of x, we're going to go ahead and just plug in some values. And anytime we are looking at a new type of graph, typically what we do is just start off by plotting some points. So I'm going to plug in these x values, and I just chose some values here. I picked these. These aren't something that I would assume you would know, but just kind of starting with some numbers around 0. You know, a few numbers in the negative direction, a few numbers in the positive direction, and then plugging it into this equation here. Well, 2 to the negative 3, remember if you have a negative exponent, then that moves it to the bottom and becomes positive, so that would be equal to 1 over 2 to the third, and 2 to the third is 8, so 1 over 8. Okay. Similarly, 2 to the negative 2 power would be 1/4, 2 to the negative 1 power would be 1/2, 2 to the 0, well, remember that anything to the 0 power would be 1. 2 to the first power would just be 2. 2 to the second power, well, 2 squared is 4. And then 2 to the third power is 8. And so hopefully you're making an observation about these values here. We have 1 over 8 at negative 3 and 8 at 3. 1/4 at negative 2 and 4 at 2. And that's going to be a pattern you're going to continue to see. So we can go ahead and plot these values. Negative 3, we get 1/8. That's super close to the x-axis, but not quite touching it. At negative 2, we have 1/4, again close to the x-axis but not actually touching. Negative 1, we have 1/2. At 0, we have 1. At 1, we have 2. At 2, we have 4. And at 3, we have 8. And so we can see this shape of our graph kind of taking place here. I could plug in further positive values. It's going to keep getting steeper and steeper and steeper. And I could plug in really negative values. I could plug in negative 10, negative 100, negative 1,000,000. And it's going to keep getting closer and closer and closer to the x-axis, but it's never actually going to touch it. So like we saw with rational expressions where we had an asymptote, we are also going to have an asymptote with exponential expressions. You will always have a horizontal asymptote, and in this case, it's at the equation y equals 0. Okay, so at y equals 0, let me go over that in a darker color here. we have this horizontal asymptote. It's getting closer and closer and closer to it, but never actually touching it. Let's go ahead and look at this one here. Here we have 1/2 to the power of x. So here where our base is a fraction, remember applying this negative, and I'll go ahead and show my work here for this. If I have 1/2 to the -3 power, well, remember we have 1 to the -3 then, and 2 to the -3. 1 to the -3 is just 1. 2 to the -3 is going to move up and become positive. That's going to be 8. So that'll be 8. Similarly, 1/2 to the -2 power will be 4. 1/2 to the -1 power will be 2. Anything to the 0 power is 1. And then 1/2 to the first power is just 1/2. 1/2 squared is 1/4, and 1/2 cubed is 1/8. So plotting those values, at -3 we had 2, 4, 6, 8. And then at -2 we had 4 and 2 and 1, 1/2, 1/4, 1/8. And so you can see a similar shape. And the same kind of thing happens. I could plug in higher and higher x values. It's never actually going to touch the x-axis. It's just going to keep getting closer and closer and closer. So again, we have that horizontal asymptote at the x-axis there, the equation y = 0. And that's what our exponential graphs are going to look like. They're pretty much all going to have this basic shape. It looks kind of like a curved L. Now, if as we move from left to right, my function is getting larger, this would be a growth. And if as I move from left to right, my function is getting smaller, then that would be a decay. So we have growth exponential functions and decay exponential functions. And we'll see a lot of real life modeling with these types of equations. Here's just kind of a review of those exponent rules. If you have something on bottom, it can move to the top and become negative, or vice versa, it can move down to the bottom and become positive. And then right here we have kind of some summary of what I was just explaining here, where if our base is bigger than 1, so if the base of my function is bigger than 1, so 2 is bigger than 1, then that means it's a growth function. And if my base is between 0 and 1, so like a fraction between 0 and 1, or a decimal between 0 and 1, then that would be a decay function. The other thing that we're going to see more and more in exponential and logarithmic functions is the natural exponential function. And we've talked about e a little bit in this course already. Remember, e is approximately 2.718, so on. It goes on forever, kind of like pi, where the decimal goes on forever and does not have a pattern or anything like that. Again, this is the natural exponential function, so we will be using that quite a bit. Now these first couple examples here, it says to determine if the following functions are growths or decays. So first off, we can look at our base, and that'll determine whether this is a growth or decay. The only kind of caveat to that is if we have a negative exponent, and we'll see that in a couple of these examples. So my base here, 3/2, that is bigger than 1. My exponent is positive, so that means this is a growth. The next one, 4/5. Well, 4/5 is less than 1. My exponent is positive, so this would be a decay. Here, my base, let me see if I can zoom in and make this a little bit clearer here. My base is 2, but I have a negative exponent. I can rewrite that as 2 to the -1 to the power of x. And 2 to the -1 is the same thing as the 1/2 to the power of x. So even though my base is bigger than 1, because I have a negative exponent, it switches it. And that means that this is, again, a base of 1/2, so this is a decay. And then here I have 1/3 with a negative exponent. Not sure why it's so hard to read. Hopefully you can see this okay. 1/3 with a negative exponent, we can rewrite that as 1/3 to the -1 to the power of x. Pull that negative inside. And -1 as my exponent on 1/3 changes that to 3 to the power of x. So even though this indicates that it would be a decay, because of that negative exponent, it switches, and it's a growth. hopefully that is pretty clear there. Let me go ahead and zoom back out here, and we'll go ahead and move on to the next page. And what we're going to do here is compare some of exponential functions that are already graphed. So we're going to compare these equations here. And let me go ahead and just kind of label them a little bit clearer. If your notes are printed out here, some of them are mislabeled. This blue line here, I'm going to go ahead and just draw over them all really quickly here. That way we can match them a little bit easier. All right, so first off, we have 2 growths and 2 decays. This right here is a decay and a decay. As you move from left to right, they're getting smaller. And the closer the number is to 1, the flatter your graph is going to be. So these are both the decay functions here, 1/2 and 3/4. And whichever one is closer to 1 will be the flatter graph. So this right here is j of x. It's flatter because 3/4 is closer to 1 than 1/2. H of x here is my other decay function. It is not quite as flat as this blue function here because this is closer to, or is further from 1 than 3/4. You could also kind of plug in some points. If you plugged in -1, you'd get 2, and that's about where this is. This orange one, between these 2 growth equations here, 2 is closer to 1 than 7, so that's flatter. This green one is flatter than the orange one. But this larger base means it's going to grow that much faster. If I plug in 1, I'm already up at 7. 7 to the first power is just 7. So this one is g of x, and it's growing very quickly with a base of 7. And then f of x is this green one here. Okay, so just to kind of compare some of those graphs. Now, like we've seen with almost every different type of function we have looked at this semester, you can shift, stretch, shrink, reflect, do all kinds of manipulations on these types of graphs. And so we can see here that a vertical translation, we're adding something on the end or subtracting something on the end. Or if I add or subtract in the exponent, that's a horizontal shift. Again, if it's plus something in the exponent, it's actually moving to the left. If it's minus something, it's moving to the right. Okay. And then a negative out front or a negative inside, a number out front and a number inside. Those also are our vertical stretching and shrinking and reflections. So now we're going to get into actually graphing some of these. Okay, so our first example, let me see if I can make this a little bit clearer here. Super blurry. There we go. Okay. So we have 1/3 to the power of x. Now, when I was graphing these on the previous page, I was using, I think 7 points, -3 to +3. I'm not going to do that every time here. I'm going to use -2, -1, 0, 1, and 2. And if I don't actually need to use all of those points to plot it. Really what you need is 3 points. So if I plug in -2, 1/3 to the -2, well, that negative is going to flip it, and then the 2 will square it, so that'll be 9. Again, 1/3 to the -2, that becomes 1 to the -2, and 3 to the -2. 1 to the -2 is just 1. 3 to the -2 is going to move up and become a positive exponent, and that's 9. Okay. So that's kind of the scratch work for that. And then similarly, this will be 3. Anything to the 0 power is 1. 1/3 to the first power is 1/3, and 1/3 squared is 1/9. So we can go ahead and plot those points. -2, and we're going up 1, 2, 3, 4, 5, 6, 7, 8, 9. And then -1, we're going up 3, 1, 1/3, 1/9. And we can go ahead and draw that graph. And whenever you're drawing these graphs, make sure that you include the horizontal asymptote. It's really important that you graph that as well, because that's part of what's guiding your graph here, is that horizontal asymptote. All right. Let's do some more examples here. And in number 2 here, we have 3 halves to the power of x. So this is pretty close to 1. We're going to have a pretty flat graph here. And I'm going to start just using a couple of points. I'm going to use just -1, 0, and 1. If I plug in -1, -1 essentially just flips this and I have 2/3. Plugging in 0, anything to the 0 power is just 1. And then plugging in 1, I have 3 halves. So -1 2/3, 1, and 1 1/2. If I wanted to, I could plot a few more points. If I wanted to do -2 and +2, again, you can do more points. You can always do more, but at bare minimum, you need to have 3. So plugging in -2, again, that would flip it, and I'd have 4/9. And then squaring this, I would have 9/4. Well, 4/9 is a little bit less than 1/2, and then 9/4 is a little bit more than 2. And so you can see, because that base is pretty close to 1, we have a pretty flat graph here. Don't want to forget my horizontal asymptote. Okay. And that is our graph. Now the next example, we're going to be graphing the natural exponential function. And I'll go ahead and just keep doing 5 points. I might not plot all of them, but I'll at least make a table of 5 points. -2, -1, 0, 1, and 2. And here you're going to want to use a calculator, and you're going to need to get a decimal since E is a decimal. So plugging in -2, -2 times 2 is -4. E to the -4 power is 0.02. Again, you can plug that in your calculator. -1, -1 times 2 is -2. E to the -2 power is 0.14. Plugging in 0, 0 times 2 is 0. Anything to the 0 power is just 1. Plugging in 1, 1 times 2 is 2. E squared is 7.39. And then plugging in 2, 2 times 4, or 2 times 2 is 4. E to the 4th power is 54.6. So that point's way up there. I'm not going to plot that one. But -2, super low, really close to the x-axis. And then -1, 0.14, again, really low, close to the x-axis. 0, we get 1. 1, we get 7.39. So up 1, 2, 3, 4, 5, 6, 7, a little bit more than that. So you can see how quickly this graph is growing. It's very, very steep. It's like the opposite of the one we just did, where it's a super flat graph over here. Here we have a very, very steep graph. And again, not wanting to forget my horizontal asymptote. All right, moving on to number 4. Now we're going to start having some shifts in our graph. So this -2 on the end here moves my graph down 2. So what I recommend doing is making a table with x and then the function 1/4 to the power of x without that -2 on the end. And then we'll use those points and then we will shift them all down 2. So I'm going to use, I'm actually just going to go with 3 this time. -1, 0, and 1. And plugging in -1, 1/4 to the -1 power would be 4. 0, well, anything to the 0 power is 1. And 1/4 to the first power is 1/4. So I can plot those points, -1 and 4, 0 and 1, and 1 and 1/4. And then all of those points are going to move down 2. So down 1, 2, down 1, 2, down 1, 2. And a vertical shift like that moving down also moves our horizontal asymptote, instead of being at the x-axis, moves it down 2. So now it's at the equation y equals -2. So we can go ahead and draw that line through the points that we got when we moved them, and that is f of x. Let's do one more. And here we have a horizontal and a vertical shift. Remember, inside it's the opposite of what you think. Plus 1 actually moves left 1, and then the minus 2 is down 2. So we're going to make a table of points with 4 to the power of x. I'm just going to use those 3 again. Negative 1, 4 to the negative 1 would be 1/4. 4 to the 0 would be 1, and 4 to the first power is 4. So I can plot those points. And then I'm going to move all of those points left 1 and down 2. So each of those points moves left 1 and down 2. Left 1 and down 2. Left 1 and down 2. And that also means my horizontal asymptote moves down 2. Moving it left and right, if you have a horizontal asymptote, moving it left and right doesn't really change it, but moving it up and down does. So, with those new points, there is k of x. All right, so that is graphing exponential functions, and what we're going to do next is doing some of the applications of exponential functions. You're definitely going to want to have a calculator, and this is definitely one of the more applicable topics within any math course, but particularly this one. Here we're looking at compound interest, and so this is how money grows in various accounts. So if I were to say I have $1,000 and I'm going to put it into a savings account. When I first put the money in, no time has passed. I just have that initial investment, however much I put in. After 1 year, I can have what I put in with the interest I earned. So whatever R is, that interest rate. Okay, so P is the principal, it's the initial amount of money. A is what's called the accumulated value. That's what you have after a certain period of time. And then after more and more years, we can calculate what interest we would have earned over that many years. Now, that is assuming a simple interest where you're just calculating the interest one time a year. However, we can have different accounts that calculate your interest more frequently. So let's say, for example, you have 2 banks that are competing for your business. You have $1,000, you want to put that $1,000 into a bank account, and so you're wanting to find the best deal for your money and whatever account is going to make you the most amount of money. So what you want to do then is figure out, which account can earn it faster. So typically, whichever account is going to calculate your interest more frequently, that's called compounding your interest more frequently, then that's going to be the account that's going to earn you money faster. So in this formula here, we have P being our principal, our initial investment, R is our interest rate, N, both of these N's, is the number of times a year your money is being compounded. And then T is the number of years your money is in the account. So let's say you have 2 banks competing for your business. One says, we'll compound your money once a year. And then this competing bank says, oh, we want your business. We will compound your interest twice a year. So now, with the first bank, you'd put your $1,000 in. Let's say they have a 5% interest rate. Then they calculate your 5% interest at the end of that 1 year. But the other bank is going to calculate your interest twice a year. So they'll calculate it after 6 months. And then at the end of the year, when they're calculating your interest again, they're not just calculating that basic from just $1,000, they're calculating it now off of also what you earned in interest at 6 months. So then the other bank comes back and says, okay, well, we'll do it 4 times, and back and forth 12 times, whatever. And they're competing for who's going to do it more frequently. Well, whoever's going to calculate your interest more frequently, if they're assuming the same interest rate, is going to be able to give you more money, because the more frequently you calculate your interest, the faster your money is going to grow. Now, most banks don't work that way. Most accounts don't work with just calculating it once or a certain number of times a year. Most of them use what's called continuous compounding. And this is compounding faster than every trillionth of a second. So instantaneously, constantly compounding your money. And notice that in this formula, there's no end value because there's no number of times we're compounding it. You have your principal, the E, the number E, your rate, and then the time. So what we're going to do in this next example is we're going to compare $5,000 invested for 10 years with an interest rate of 6.5%, compounding semi-annually, quarterly, monthly, and continuously. And so what we're going to look at here is I'm going to set up the formulas, our respective formulas for each of those, and then you can type them into your calculator and see which one's going to give you the most money. So semi-annually, that would be 2 times a year. Quarterly would be 4 times a year. Monthly, well, there's 12 months in a year. And then compounding continuously would be this formula here. So using both of these formulas, the first one, A is equal to 5,000, our principal, and then 1 plus my interest rate, which is 6.5%. So 0.065, you want to write it as a decimal. And then it's compounded semi-annually, so that would be 2 times a year. And then my exponent would be 2, again, because our end value here, and then the number of years, which is 10. And then you can type that in your calculator. Now I'm going to set all of them up first, and then I'll type them all in my calculator. For B, our accumulated value will be equal to our principal amount, $5,000, 1 plus 0.065 divided by 4, our number of times we're compounding, and then to the power of 4 times 10. C will be our principal, 1 plus 0.065 over, and now 12 times a year, and then 12 times 10 here. And then D is where we have that different formula, the accumulated value, our principal, and then E to the power of our interest rate, 0.065 times the number of years it's in the account. So typing all of those into our calculator, again, making sure you're following order of operations and doing things correctly. For the first one, you should get $9,479.19. For the second one, you should get $9,527.79, so already an increase. As we would expect, the more times we compound our money, the more money we're going to earn. And then the third one, $956.09. And then the last one, we'll have you know what? I think I just copied that last one down wrong. Let me check that real quick here. 9,577.70. So that last one, part C, when I did my calculations, I think I wrote that down wrong here. So let me check that real quick. We have 0.065 divided by 12, and then plus 1, and then raised to the power of 120, and then that times 5,000. Yep, that should have been $9,560.92. There we go. All right, so we can see that the amount we're earning each time is increasing with the more frequently we're compounding our money. And that brings us to the end of part 7 of Unit 2, and then in the next video we will look at logarithmic functions.